So the challenge is whether I want to record more board or to share the slides. So let's still record. Yeah, record the board mostly. So the general topic for today is system calls, but let's quickly finish the what we were doing, the very first process. But I just figure out my slide. So remember what we were doing last time. So we said we were thinking of how to create a first process, right? And so the idea was that on top of a microkernel, like there are different possible ways to do it. So which way we should discuss. But the idea was that just maybe quickly we covered the main function, which I didn't for last time. But the idea was that if we have a microkernel and we try to create the very first process, like essentially, remember we started executing the main function in the microkernel, and that's what we had on the board here last time. And we do various parts of initialization like DBT, IDT, memory allocator. And finally, we said, okay, we're going to create process 0. And we were discussing what's involved here. And the idea, a couple of main ideas is that, well, obviously, we need this probe data structure, and we will construct the address space for this process, right? And meaning that this will have like a page table which describes the address space. And there are different ways to do it, but probably like the map function which you guys are building as part of the homework can be used here, and we can run it in a loop. And essentially, if we need a new virtual address map, and we also agreed that our virtual address space will always contain some kernel part. This is virtual, and this virtual will map all available physical memory one-to-one, right? And the upper part of this address space will be reserved for the user. So essentially, starting from this, we were calling this user base. We will be loading L files. So this will be mapped with only 3 or user privilege, and this will be mapped. This part will be mapped as range 0, right? And so essentially, every time we create, right now, like we will probably have to create kind of like a dummy address space before we're creating the first process, because the question to solve here is that what happens if this very first process gets terminated? Maybe it creates like a page fault and the kernel just simply says, okay, you cannot run anymore. So we still need some address space to keep running. And again, you can solve it differently, right? But it seems to be normal to maybe have a default kernel address space, like from address 0 to some max here, right? But every time we create a new process, we said, okay, again, it will be 2 parts. We'll essentially copy the kernel part of the address space, this one. And so this page table, in fact, the page tables can share this upper part, because why not? We see the idea. Then we can like essentially share those. If we have a 4-level page table, for example, and we say, look, when we create a new address space, really the upper part, the slope or the kernel part of the address space can be shared, right? The subtree can be shared, because well, that's probably a clever optimization. I don't see a problem with this, right? But then when we start loading the L file, we'll start essentially mapping pages from user base. I mean, depending on how the ELF is linked, and we can deny like we can check it and say, look, we're not going to load something because if it's mapped, if it's linked to run here, we'll deny it. We only will be allocating space above the user base, right? So then we will create a private part of the user, the user part of this address space. This makes sense, right? Any questions? All good? Okay. Okay, and so what we were discussing last time is how to actually get this process running. So essentially we say, look, in order to start running something, and like by convention, often this process is called main zero, or I don't know, we can call it process zero, it doesn't matter. Essentially it has to come from somewhere. And we said, okay, look, instead of like going to the disk and building the disk driver, we will instead use this idea that the grub can load additional modules, and assume that that grub has loaded some additional modules into the address space already. So like if the grub loaded the kernel itself, right, at the first megabyte, so this is the kernel binary, you can specify and ask grub to load additional modules, right? So grub itself implements file system driver, so it can go ahead and read a large variety of file systems. Read-only file system access is easier than writing, so essentially it can read some additional module, and this module will be the L file of the main zero for now, right? Makes sense, especially for people who missed, right? And so this will be sitting in memory, and essentially our idea that when we start creating the first process, we will parse the L file. We'll do kind of like I'll parse the L file, which is of this DOM 0, which is L file, and essentially we'll just follow we'll stop on it in a second, but essentially we'll load the loadable sections into the address space of the process. And at this point, we can use the entry point from the L file, and at some point we will exit into this process, making sure that we switch into ring 3. There's an IRET instruction and start running at the user level, right? Make sense? What I wanted to say. So there is this subtle problem here that, remember, up until now, and in the homework instructions, I said, okay, use this AND symbol and use this area above the kernel, this page array, to keep track of, to implement our memory allocator, right? Unfortunately, we cannot do immediately this, because if we have a module, then it may partially overlap with this AND area, might not overlap at all, but then accidentally, if we missed, we can just, if we start allocating memory, maybe one of these pages or some of these pages get allocated, used for page tables, get overwritten, so we will lose our L file, right? So what's the trick? What can we do to solve this problem?
Just change the order.
Yeah, so what you're saying is that, sure, we can, and like partially this overlaps with the homework instructions, we will maintain a logical AND. And essentially we say, look, instead of like allocating page array right immediately about the kernel, we'll first copy this L file here and then set the page array above it, right? That kind of makes sense, and it's the easiest approach, right? Because like as we move forward, there might be some additional data structures which we'll want to put in front of page array as well. We'll talk about it a little more. I mean, I can guess that it's coming, but I don't know for sure what the correct answer right now. Alternative approach would be just if we can verify that the page array actually fits before the DOM elf, we can mark those pages as unavailable for the allocator. Then we don't have to copy it. I mean, it's a little more complicated. So I would suggest let's just copy. Like unless you're implementing some very fast boot protocol where you count every whatever microsecond, right? Then you just copy. This domain 0 can be large. It can be like megabytes, right? Because we will obviously it's not just the L file, this process, like, because maybe we want to create process Q1 or Q2 or whatnot, right? Depending on how far we want to go this route. In this class, probably just 2 will be enough to implement some kind of IPC. But if it's a real operating system, that can be a real file system, like some in-memory file system, which keeps all of them together, right? Which is kind of smart to build, but yeah, so it can be like, even on embedded system, it can be some sizable chunk. I don't know, like you should evaluate whether copy is a viable solution for you or not. But in our case, I think it's okay. It will simplify implementation. Make sense? Right? So we solved this problem, and where we left last time, I was showing this diagram of the L file. Let me just quickly start the slideshow here, just to reiterate that we understand it. Let me share my screen as well. To reiterate that we understand, I'm sorry, that we understand how the ELF works. And I mean, we did some refresher of the ELF file real quick, but also I wanted to make sure that we have a good understanding. Where is it? Here. Okay, again, like it's a little, I don't really know, guys, where you are with ELF. So we covered ELF quite well in the x86 class, and we did a homework. We did 2 things, because remember last instance of the class, and I don't know which year you took it, we accidentally leaked the homework assignment, the solution to the homework assignment, which was just loading the ELF, right? And so this last year, we built a new homework, which was actually, instead of just loading the ELF, was asking you to perform relocations, right? Do you remember this, or vaguely? And this homework has reasonable instructions. So who did the homework? Was the relocations? Just 2 people, so no one. Okay, cool. Then maybe like just short overview. Okay, who did the homework on loading the ELF? You guys never took the x86 class at all?
Correct.
Jesus, I mean, I'm surprised that you're still holding. I mean, I actually was under impression that majority of people did take the class. But when I say this is how x86 does it, you have no idea, right? Because you never had a chance. And that's fine. I'll try to refer less to x86. But it probably makes sense for people who did take the class. How do we go about it? I apologize, but do you plan to take it in the future, or what's the plan? It kind of, I mean, yeah. It depends on what you choose for your career. You kind of advocate that if you want to stay in this field, depending on how well you understood everything here, maybe it makes sense to either rewatch the videos, x86 videos, or just take the class for one or another. Because it will kind of complement this class with, because a lot of this assumes that you already know how x86 does something. So you can use it as a concrete reference of how you can load an ELF, for example. But there are different ways to learn it. Okay, so let's quickly brainstorm how we can load the ELF file. And especially someone who took the class, can you just give us a narrative of how this ELF loading should be done? Like by looking at this diagram. And if you don't understand the diagram, let's quickly spend some time and I will review it for you. Because wants to go. Do we understand the diagram, ELF? Okay, let me go then. So ELF, as I was trying to explain last time, I mean, all of these formats are relatively simple. It's kind of like, they all have a header, right? And in the past, this header was saying, okay, here's an offset for the sections which should be loaded in memory, like a text section, data section, better safe space section, BSS, right? And that was A out, right? On Linux, when you generate a static binary, it has a .a extension. That's for this A out format, right? It was very simple, so but it was not flexible enough because people said, okay, really, we want two views of the binary. One is for loading, just load in memory and start running. And second for linking, loading, and relocating. Relocating means that you can compile a binary and then you have enough information about the binary and so you can shift it in memory, like essentially relocate to a different address, which is like, why would you do that? Like really, the original reason is that when you have dynamically loaded libraries, if you have a conflict and they are linked to be at the same to overlap, like essentially have something like essentially you have a DLL on Windows or SO shared object on Linux. If they overlap, that kind of creates a problem. And so if you have a position independent code and you can essentially relocate them, then you can just like freely pick an empty spot and just solve this problem, right? So essentially, you just have enough information to strip this or any of those in any possible way, right? Question.
Does this relocation also mean like inside of this address space, relocating things arbitrarily like for security reasons? Because like, if you know the location of the buffer and it's the same every time,
Correct.
That can be bad.
Correct. So, but the original reason was just to avoid this conflict. The second reason in the most recent systems is address space layout randomization. So you can randomly choose the base address for the binary, and it's somewhat complicates exploitation, but with modern means, it does not complicate exploitation by a lot. You can go in depth with this technique and say, look, we'll be really splitting this binary individual blocks, functions, or even smaller, and then randomizing those guys all over the place. Then it complicates exploitation as well, even further. But I think it's still, people learn how to recover it, but have an expert. So, but coarse grain address space layout randomization will not stop an attacker, although it is used on most systems. I think it's all on by default. And like, usually you have to turn it off to make the stuff debuggable, otherwise it's just too hard. Great. So that was the first reason essentially. And for that very purpose, they said, okay, we will create a newer format, which is not AOUT, but this ELF. ELF stands for executable and linkable form, meaning that executable stands probably for the fact that you can take it, just load in memory, and linkable or relocatable means that you also support not only like moving those things in memory, but also if you say, look, I have a shared object and it depends on another shared object, there is enough mechanisms like global offset table and stuff like that, and PLT table to essentially kind of stitch them together lazily later when this stuff is like loaded in a single address space, in this address space. But meaning, and there's also support for the fact that imagine it's libc, so you can load it in memory essentially once, and then map it in multiple address spaces, and it will show up possibly even at different addresses, like at different bases, like D1, D0, D2, in each address space. And the code is also compiled in such a manner that it can actually execute correctly, irrespective of the address at which it was mapped. So essentially, this text section is read-only mapped in all address spaces, which means you don't have to change it, but it can show up at a different address. But it essentially, there is like tiny private part for each address space, which is writable and different, but this part is smaller, so you can share text sections of libraries. And that's essentially the main motivation for shared libraries. So you can load libc once in memory, right? Make sense? And essentially ELF supports these two views. And that's why here in my diagram here, I have arrows of two colors. So green and blue. So the green ones are like, again, historic names, because before the page tables, segmentation was used for marking sections as like choosing the bases, like and stuff like that. And so it's sections. So essentially, this is for the green arrows are used to just load the binary in the memory and start running, whether the blue arrows contain enough information to relocate or relink the binary if it depends on other libraries. On other libraries, or has to be shifted in memory. And roughly speaking, both of those go like this. So there is a pointer in the header to the table array, which contains pointers to other sections, whatever, which has to be loaded in memory. So in my example, I think I have like 3 green sections. So this is 1, this is 2, and this is 3, and they all have to be loaded in memory for the binary to start running. So one is that executable sections like image and text, writable data section, read-only data section, if you just want to change the flag between writable and read-only, affect the read-only section. There will always be ESS section as well, which is not stored but is expanded in memory. And if you want to relink the file or essentially or relocate it, there will be a second pointer. And historically, there is a second array, which usually sits at the very end of the L file, which is called the section header table. And this section header table essentially contains enough real information that you know each, like for example, if the green one merges init and text together, they say it's just really you just treat them as executable code. Then the blue one allow you to distinguish between those two, and you can treat them separately. But what's important, it also has information about relocation symbols. So really you can shift this binary in memory. And we can go over this position independent code, but I mean, I think I cover it in x86, so I don't really know to go over it again, but it's your choice, yes or no. But okay, let me stop here. So this is the L file. The kernel itself is an L file. Domain 0, which we will compile, is also an L file. But we have a power to make sure that whatever we compile follows certain rules. And these certain rules can be, say, we just want a binary which we can just simply load in memory. For example, right into this user base address and just start running it. No relocation, no linking, nothing. And again, in a real operating system, you probably would do it differently. And we can take a look at how relocations are done. But unless we have a lecture on relocations, we don't really know what to even expect it. So I would just say, ideally it's material of this other class, and whoever wants to take it will take it. Whoever took it already can review. But essentially, the easy way to make sure it works is compile it as a static binary, which is ready to go at a specific address. Make sense? And this is what x86 does. So essentially, processes in x86 they do this trick, although they compile them from C, but it's the same from Rust, more or less. Make sense? And so I suggest let's do it. So okay, unless we want to dig into how relocations work, which a real operating system would have to do. But again, if you ever in a business of building one, I don't think it will take you that long to figure it out. So like maybe a couple of days of reading. And examples are available all over the web. So the 5460 has a homework. I think I would say it's homework either 2 or 3, probably 2, which asks you to relocate. So instead of a static L, it's relocatable L file, which will ask you to relocate correctly. And there is a sample Rust code which I can show you. Okay. If you've never seen how L files are loaded in memory, let's just again spend 2 more minutes on this loop. So you kind of understand what needs to happen. So you know, I mean, I did not explain it very, very deeply, but again, L header contains something like an edit number, entry point, which says, okay, you want to run this program, start with this specific address, and pointers to the tables, program header table, and a section header table. And we care about this program header table because if you want to simply load it, we follow those green lines and load them in memory. So how is this loading program? How is this loading process looks like? What do we need to do? in this loop. X was 6. Anyone?
I forgot about details, but I think first. We add that. That's it. Yeah. Target paths.
No, almost there, but let me quickly give you a gist of what needs to happen. It's very, very simple, honestly. And I mean, I don't blame you for not remembering it. So this is why we're here. So look, if this ELF file has an ELF header, okay, the first step is parse the header. Essentially, say that is it really an ELF header? And the way you check is that it will have a magic number here. And what you do is to say, okay, is it really that magic I'm expecting to see? If it's so, then we believe that it's an ELF. There is no checksum, I don't think so. So when we have an ELF header, the next step is to figure out this pointer to this program section, to this essentially green lines. So program header table, which we read from the header, and essentially it's located somewhere within the ELF file. This is just an array, and we're looking for entries which have something like a load flag, because there are some other entries and you can just simply discard them. And so essentially what we do here, each of those entries with the load flag will have a pointer somewhere inside the ELF file, where, for example, the text will be, or the data section, right? And so essentially you create a loop, which after you located this part, so you will say, okay, I have a program header table, I know the pointer to the beginning. Now I loop through this and I'm searching for the entries, and entries are of a fixed size and well-known layout, nothing is dynamic. And you're looking for the ones which are load, and essentially you figure out like each of them one by one, and there will be an address at which this section has to be loaded. And here you should check that this, I mean, first of all, they can be out of order and you have to keep track of where you loaded something. But essentially, at least the minimum invariant you should enforce is that all of them are above the user space, right? And every time you try to load something, say, look, this specifically, this specific section is sitting somewhere on this in memory loaded by graph, right? So your goal is to, roughly speaking, copy it into those memory addresses, right? Right? So nothing, let me actually stop sharing so like the board is more visible. What we need to do, obviously, you need to allocate those page tables, or the pages for this address space. So every time you start every time in this loop, you figure out the section, or like whatever this segment. No, this is called, yes, segment. You say, look, I will go to my address space and I will map this region, right? And the moment it's mapped, you have kind of like a virtual address here. At this point, you can just do a simple copy from here. And you have, since you know where it's within the ELF, you know the from address, and this virtual address is a to address, right? Make sense? And at this point, you just copy from here to here, right? Make sense? And you keep walking and you set the flag. So this might be read-only executable. The next section will be writable, and the next, or they can be out of order, they have gaps, because whoever compiles this ELF file controls how it's compiled, has a linker script, whatever they want to do, they can overlap And at this point, either your map function should return an error, or you should keep track of the layout of the address space. I suggest that the map function can return an error. Or you can just even proceed and say, look, maybe I will end up with an incorrect ELF the moment it starts, as long as it's above user base and map, of course, like below the max available address space, you're fine to do whatever you want. It can crash later with a page fault, or maybe user wants to do something funky. Again, like we can discuss security and variance here, but we can also kind of blindly go forward, right? And one additional thing is that there will be this BSS section. And the BSS section, I forget exactly how it's defined, but it's somehow almost like it's beyond the ELF file, like it doesn't exist. Right? So because you say, look, I know that it has to be mapped here, but it's not in the file. And you just like again map the pages and just fill them with zeros. Because BSS is the one with just like zero initialized. That makes sense. So that's essentially our loading. And at this point, we will pick up the entry, from the ELF file. And this entry will be our entry point in this process. Great. And we're kind of almost ready to run. What else is missing to start running this process? You will context switch, and we discussed it a little bit last time, but that we can, if we have this proc data structure, which we created somewhere here, which has this pointer to the page table, so it has a proc. So we can create some context of execution, let's call it context. Start like where IP address, we should set it to the entry point, right? And then when we exit into this process after the context switch with an IRAT, this will be the value of the instruction pointer, which the IRAT will set, right? So that's correct. But again, this thing technically can run, but most likely will crash unless you do make additional assumptions about how you start your processes. But typically, like enemy, again, not set in stone, but let's like what else is x86 doing? It's not hard, so you should. What is it? What are the parts of execution environment of a simple Unix process? What else do you need besides text, read-only data, writable data, DSS to start running? Stack. Right, because I mean, and this is where I'm saying, like I'm mysteriously saying that it's not set in stone. It's a POSIX convention that you will start with a stack. You can very well say, look, guys, I mean, we're gonna start without a stack. And one of the very first things which this process has to do is to go back in the microkernel with a system call and allocate a stack, right? And to be honest, maybe we should follow this approach, because why not? Then it will allow us to create, then we don't even fix the address space. We just simply say, look, we loaded the ELF. If you want to have a stack, so just have a tiny trampoline, assembly trampoline, which invokes the syscall, which allocates additional memory and sets it as a stack for this execution environment. And they have full flexibility of how big the stack should be, how many stacks they want to allocate. So we don't fix the layout of the address space. So in some way, maybe that's even a better convention than what x86 and POSIX is doing, right? I don't really see a reason to have a stack unless what? Why does the POSIX need a stack? Do you guys remember?
Say the return address of the
Well, yes, but this process, do you expect it to ever return? And if it can return, where should you return? So there's really no good way to return. a good way to finish the process is to say exit, essentially, they say an exit system call, and the microkernel will terminate this process. So, no, I mean, you're right. Normally stack is used by the compiler to save return addresses, so you can return just in general build computation. But roughly speaking, it doesn't like contradict our idea. If we have a tiny ASM trampoline here and then start executing the C code only after we set up the stack, we can very well do it. Like nothing will get broken, right? I'm still kind of pushing that this idea makes sense, but POSIX uses stack for something else. What else is there? You remember? It's almost like a job interview, except that everyone would be hyped and well prepared. Now, like, think about it. Why is it stack?
Just kind of give it down to you.
Not sure I got what you said, but probably the answer is no, because I mean, I'm not saying that we're not going to have stack. I'm just saying we don't necessarily need a stack on startup. So meaning that in this loop, I kind of argue do not allocate the stack because it creates additional burden to have to allocate it. Maybe we will fail to do it correctly. But if we say we just start running and require each process to have a tiny assembly trampoline, which doesn't push anything on the stack, doesn't touch the stack register, which invoke the syscall, which allocates the stack, and then sets up the stack register to RSP to point with the stack. Then everything will work, and after that you can execute C or Rust here, or any other language. You had an idea? But what I'm asking is that in POSIX, this stack has to exist on the start. I'm asking why, just to make sure that we remember this design choice. Did you have an idea?
Bad things happen if there's a stack when you're not.
Well, of course, like if you immediately start executing C and this C pushes something on a stack, then because if you compile your main function in C, maybe this very first thing pushes like EBP or something on a stack, right? So that will crash. But if we're careful enough and make a contract with userland saying, okay, we don't have stack when you start, so do whatever you want, you have to allocate it. And then userland can run a tiny ASM trampoline, set up the stack, and then call a main function, which is stock C.
Just want to have interrupts.
Why interrupts? This stack is not even involved in the interrupts. For interrupts, we have to create possibly a kernel stack, which will be like a pointer from this process data structure, but it will be a kernel stack.
Yes.
But as I said, we're designers of this system. We can say no, there will be no stack.
Is it because we have to pass function and
Correct.
probably local variables?
Correct. No, POSIX says, okay, when we start a function, main, they made this design choice, which is not bad. They say, look, main will allow you to take this argv array of arguments, and I forgot exactly RC is the size of this array, right? And they say, look, guys, even if on some architectures, these two can be placed in registers, like for example, on 32-bit, they will be already, those arguments, the C function expects those arguments to be on the stack. But what's more important is this array is an array of strings. So like you can say like, okay, cat, who gives me, and also like process, the name of the program itself. Right? So that was their way to pass arguments from the shell. And the contract was that the arguments are just strings, and it's an array of strings. Each string is passed on a stack. Yes, not that I read the standard, I now can, maybe it doesn't actually say that it has to be on a stack. Maybe, okay, sure, maybe I'm wrong, but essentially the convention is that this is usually passed on a stack, right? But, or alternatively, then you have to create some space to pass this arguments. And, okay, but where I was heading is that if we abandon this convention, essentially that the process takes array of arguments, then we don't really have to allocate the stack. I mean, when I stumbled just a second ago is that I kind of, because everywhere I've seen those guys were passed on the stack, but maybe POSIX is flexible enough and say, look, this doesn't matter. So as long as you have those arguments elsewhere, like maybe create an extra section in the L file and pass those here, then you can again avoid even creating stack in POSIX, but I don't know for sure. But here in our system, we can make a design choice, and it's a sound design choice, not to pass arguments on a stack, and we can avoid creating the stack. Why is it a sound design choice for us? Like, the question is like, to be usable, do we really need this convention, or what else do we? How else we can go about it? Remember, we're building a microkernel. And trying to make interfaces simpler and everything.
Suppose if we're not recalling any particular process.
You're right, but on the other hand, one can push, and in fact, you can probably very quickly run into a case where you say, look, if there are two processes, like, and let's call them a parent and a child. And the parent has something, I mean, some piece of information, and it wants to pass it to the child. Think of a programming language, you create a new class, you probably want to pass something in the constructor most of the time, right? Otherwise, those classes are not very useful and can be there. How can we pass this something into a child in a microkernel? And like to make it more specific, because it's hard to answer this question. We talked about the IPC mechanisms, kind of like pipes. So glorified pipes, which we're going to build. So what is a different convention we can implement to make sure that the parent can pass something to the child? What do we need for that?
We just save it and share space.
Yeah, we can say the child always shares some region of memory with the parent. Maybe it's not ideal, although it's also a design choice. But imagine you have something like a pipe, and I will draw it as this, and I will call it an IPC endpoint. And because typically this is how people call it. And roughly speaking, the parent and a child don't have to initially share anything besides the fact that they can share this endpoint. And then, they can later play a protocol by saying, okay, I'll send something here. So think of it as a pipe in x86. And this guy says, I will receive something or read something from this endpoint. And if you want to pass those strings, like whatever we have cat, whatever, txt, we can just pass them through this endpoint. Then there is no convention. Like, it's a slightly, I would say, it's a simpler and lighter way of saying, okay, I can either pass strings, or maybe at this point, like coming back to the shared page, you can, if your endpoints support passing pages, you can immediately establish a region of shared memory and then pass large chunks of data, like terabytes or megabytes of data between the parent and a child, right? So roughly speaking,
what we need to in our microkernel, and we will have a lecture on IPC, and I'll kind of explain those trade-offs probably a little better. But at high point, we say, in contrast to POSIX, which parses strings, we don't fix anything. We say the only requirement is that the parent and the child share an endpoint. And we can, like, how do typically children know about endpoints? Think of file descriptors. And you can say that, like, when the child is created, the system guarantees that the file descriptor 0 is connected to the IPC endpoint, which connects to the parent. And in the parent, whatever, it can be like endpoint 25, it is already created 23 other or 24 other children, right? Make sense? So this way we say, look, well, first of all, nothing is shared besides this one file descriptor, which we insert into the file descriptor table, but we will call it differently later on. But think of it as a file descriptor table right now when the child is created. And from there on, they can play any communication protocol and exchange any information, right? And if the parent says, okay, I deny you, I will not talk to you, then the child will run completely isolated, kind of, right, from the rest of the system. It cannot read file system because unless we have, since file systems are probably accessible through other, like, for example, if there is another process which implements a file system, and the parent is connected to a file system with the property, connected to a file system through an endpoint, an obvious solution is to send a pointer to this endpoint from the parent to the child, and then the child can be connected to a file system as well. It's kind of like passing a pointer in a programming language. You say, look, you didn't know who implements the file system, but if you receive a pointer to the interface, then you can read from the file system, right? And everything in the process can be abstracted. So if you have enough libraries and you're coding in some nice language, then you know, like, it will be really an interface, but underneath there will be communication through the endpoint. Make sense? Okay, so my detour here was that, okay, so, and again, it helps us to simplify the implementation. For this specific class, you may say, okay, are we oversimplifying? And the argument is, I mean, we make the things simple, but they also play in practice, those things they make sense. Why is that? Because we're simplifying the logic of a microkernel, which means that there is a smaller chance of introducing a bug. And if you're building some like sensitive or security critical system, the less code you have in the microkernel, the smaller chance of introducing an exploit there will be, right? So it makes sense to say, push everything to user land. At least you know the process create system call is so simple that it's unlikely to fail. And the second argument is, if in the modern world, like even today, you can build a user verification tool to verify correctness of this create process system call. And the simpler it is, like semantically, the easier it will be to verify. And so that's why making those design choices also makes sense. So you don't have to deal with, like, imagine like someone has to pass their strings in the stack. You have to reason about strings, their sizes, that they don't overlap, that you like form this argv and argc correctly. I mean, it's not super hard, but it's a burden, right? And like, who knows, maybe you can make a mistake, right? So it also makes sense in practice to go with this design. Okay, good for now. Okay, so then what it means here is that in our loop, when we loaded everything in the other space, we don't even have to set the stack. We just really have to remember this entry. Like, we will talk about context switch and how we want to manage the context, but essentially in some notion of a context, which when we will be using an IRET instruction, returning into user level, switching from ring 0 to ring 3, this context will provide us with the user value of the instruction pointer, which is an entry point. And our agreement will be that we will have a tiny ASM trampoline, which we will call syscall to allocate a stack
right, early on, and after that, you can start running something like Rust main function here. Make sense? Yep, pushed kind of stack allocation into the like from the microkernel into the user level. Okay, I think I'm done with loading. I don't remember. I don't think I forgot anything. So essentially, we were in a loop loading like segment by segment of this executable file. We expect that it's linked and relocated to run at user base, which means that the entry point might not be exactly this address, but might be somewhere close to it, right? Because the compiler might like it can reorganize the code, but it's at least somewhere here above user base. Then we created the page table for this process, and we remembered the entry point for this for the process in the context, and the RSD value is still undefined. I don't know how you want to mark it, but let's say null, right? For now, and the user knows that there is no stack; it has to allocate it. And after that, we're kind of, I think, believe we're done with process number 0. And as I said, when it's returned from here, we'll add it to the list of, we can call it a scheduling queue. We will add this. There will be only one process, this P0 on the scheduling queue, nothing else. And by the end of this main function, we can either enter a scheduler group, or we can organize the execution a little differently. We'll talk about it, but roughly speaking, if we enter the scheduling group, then this loop will pick up this process from the scheduling queue and says, okay, look, I know that that's next process to run. Invoke a use low-level switch function similar to x86, which will set up the execution context of the CPU. And depending on how we want to do it, it will essentially exit into the user level and start executing from this user level instruction pointer, right? Makes sense? And we will end up with a system which has a running process which can start executing system calls. Make sense? Agree? Any questions? So it's still part of the boot, roughly speaking, but we're kind of getting towards the end. And the assumption is, and we discussed it last time, and since we set up timer interrupts, at some point, if we started running user level code, a timer interrupt will be delivered, which will force us back into the kernel through the interrupt handler, and we will find ourselves somewhere around the switch function, or from the timer interrupt, we'll figure out how to start switching to the next process to run. There are, again, multiple ways how to do it, but conceptually they're similar. Yep, makes sense. And then we'll start running stuff. Good. Okay, imagine we have this. So what's the next building block which we need to introduce to our kernel? What is that we want to do next? What is missing? I gave you a hint at the very beginning of the lecture. The main topic of this lecture is what? Correct, system calls. And again, like, because even here, even to allocate the stack, we need to immediately invoke a syscall, return back to the kernel to ask for certain service from the kernel, right? And sure, so the next logical step is to figure out how to build those system calls, right? And after the system calls, we will talk about the context switch and the scheduler. And after that, we'll be able to run processes. After that, we'll probably have to discuss how to create from a parent process, how we can create a child process. But by then, you will finish the homework on how to create the first process, so it will be easier to discuss. And after that, we will talk about IPC, so processes can communicate. And more or less, this is like a running microkernel. Okay, system calls.
So what do we know about system calls, guys? Let me switch the slide deck. What do we know about them? Do we remember anything?
My perception of system calls is that they're kind of like.
Correct. They're like function calls. Hold on. In fact, yeah. So they are kind of like, I mean, kind of like interrupts in the way that they switch you from privilege level 3 to 0. But on the other hand, you should think of them as function invocations across this secure boundary. So essentially, it's almost like a function call. But in order to enforce integrity of the kernel, you need to provide an entry point, because user cannot just simply call here in between, post some like checks on the arguments, right? And start running in the microkernel, then user can do anything. So essentially, syscalls will always enter through a specific entry point, and then will, like, essentially after that, you can implement any logic and like make sure that the user gets what they want. But how do we build system calls normally? I mean, what is normally? How did we do it in x86?
In x86, it's like a function call, but you don't actually jump straight to kernel space. You jump to like.
Correct. So this is the wrapper. And how do we invoke this wrapper? Cross privilege link rings. Do you remember? What are the ways to exit, or whether it should be called exit or enter, from rings 3 to ring 0? Do you remember? Know how x86 was doing? Do we know a hardware mechanism? No, no, like, okay, let me ask a question, different question. Just a second ago, I mentioned that we will use IRED instruction to exit from ring 0 to ring 3. So how did x86 enter back into ring 0? IRED as a hint. Well, and you mentioned that's correct, but you mentioned that it's kind of similar to interrupts. Like in x86, we were using an int instruction with a specific number, x40, and that essentially triggers an interrupt, very much like timer, which takes us to the interrupt descriptor table. In the interrupt descriptor table, we configure entry number x40, right? And here, there will be a pointer to this handler, to the entry point. And since the microkernel or the kernel configures the IDT, it says the entry point, and there is a specific discipline. I mean, not specific, it's the same as any other interrupt. So interrupt pushes, like, figures out the kernel stack by going into global descriptor table and figuring out the TSS entry, which is pointed by the TSS register, or TSS segment register, figuring out the kernel stack, and essentially the hardware saves the 5 things on the kernel stack, right? Makes sense? So it's exactly like a timer interrupt. Same protocol, except that when we set up this entry, we set up a specific flag saying that it's okay for the user to trigger it. Because if we set this flag for like a page fault and user starts saying in 13 or whatever the page fault number, that kind of sucks because it will confuse the hell out of the kernel, right? Because typically the page fault should be really generated by the CPU when it fails the page table walk. But here we say user can suddenly invoke those interrupts, and so user or a timer, for example. So this is only set for this entry in the interrupt descriptor table, which is reserved for invoking system calls, right? And the way we switch the rings, who remembers how do we switch the rings?
Correct. So here will be a code segment as well, which points to the entry in the GDT, and this GDT entry will be configured with privilege level 0, right? And that's how this can be invoked at privilege level 3. Then it goes to the IDT, picks up the entry code segment entry with PL0, and we start running in the kernel in PL0, right? That's how we normally in x86 configure system calls, right? That's a good refresher. So make sense? Like exactly like a timer, but just invoke from the user. And this is just one difference, that you set up the flag that the user can actually invoke this instruction. Make sense? Now the question is the following. Actually, it's not a question. So that mechanism works fine, and we can use it. I mean, I don't mind if you implement it. But as system designers, you kind of can guess that it's not ideal. So what is not ideal about it? I realize that I'm still sharing previous slide deck, so that's why you don't see the new one. But what is not ideal about it? Trying to switch to this one. What do you think? What is not ideal? No peeking.
We were talking about how like constantly having to switch to the kernel space.
And what do you think takes time? Or what is? No, you're right. So that's exactly what I was going after. That, like, typically system calls, we want to make them fast, ideally as fast as function invocations, but we have to switch the rings, right? And so, like, older CPUs had this mechanism to switch the rings. So to say, look, I will invoke this int, and then I will go through the IDT, pick up the TSS, pick up the kernel stack, and then start executing the handler. And it's not ideal because it takes roughly 350 to 400 cycles. I think even just to enter the kernel, I don't remember how long the return costs, but about the same, but maybe less. And imagine you like sending or receiving packets all the time or reading files, and in a normal kernel, not in a microkernel, it's more complicated. But the idea is that you really at this point, like executing a lot of system calls. And if you're losing 400 cycles on each invocation, and maybe the whole syscall like to send a packet, it's like less than 2000 cycles, and you suddenly like, if it's the entry, I forget exactly entry exit, but let's assume it's both, then you like 25% slower or something like that, right? And CPU designers realize that, okay, any system these days executes a lot of system calls, and essentially they said, okay, can't we design a faster mechanism which just essentially kind of like enters into the kernel a lot like a function call, but with a minimal security setup, but with a lot less data structure. So essentially bypassing those data structures, but maybe keeping the positions of the kernel stack in some CPU registers, keeping the entry point of the handler in another CPU register, and then arguably it can be done a lot faster, right? And I mean, it's hard to argue. I mean, I don't know the answer. What really takes 400 cycles and why? Because really, if you very carefully think about it, you can say, look, okay, maybe this is one like we're saving 5 things on the stack, which can be done asynchronously. We'll do look up the stack, but a lot of it can be cached internally in the CPU. So why is it taking 400 cycles? I don't know. And Intel will never tell me, but maybe, I mean, so feasibly, it seems that if you like designing your own CPU, maybe you can optimize this mechanism. But maybe there's like a tons of logic which they have to perform on the interrupt transition and check all the corner cases because they needed to support like legacy, like those entries can be configured differently. Some of them like call gates, which I don't even know how they work anymore, but along those lines, right? And really, this is where like they said, okay, forget about it. We'll give you a new one.
And this new one is called syscall, or like there was a, I mean, it's literally a syscall instruction. And the syscall instruction is a lot faster, right? Just because it like essentially abandons all of these legacy things. And essentially the argument here is that similar to all modern kernels, we will use the syscall instead of an interrupt to implement system calls, right? Just to be like up to date and not goofy. It's okay for x86 to do this, but we want to be like a little better. And at a high level, the problem is that we only have 5 minutes left, so probably I shouldn't go far into it. But at a high level, the idea is that you will, where's my slide deck? This one. Just switch to this. At a high level, you will use a couple of CPU registers, and they have funky names, and they call model-specific registers or MSRs. This is a large register space, which you access with specific write MSR instruction or read MSR instruction, giving the point with the number of this register. You configure those registers, and essentially the idea will be that we will really, the three registers are important, right? So we need to know where the entry point to the handler is, right? In the kernel, this is the handler. We will put it in one register, which is called this L star. We will need to know the code segment for the kernel, which is a little unusual because, but yeah, apparently you need to know it to enter as well. So it's kind of like a pointer to the GDT, and you're essentially picking up the code segment. This will trigger a change, PL0. One additional thing is that this really has to be PL0. Cannot be PL1. If I understand correctly, Intel only supports syscalls from ring 3 into ring 0, no intermediate rings, because interrupts can go to any ring. And at this point, and the third thing is that you say which flags in the E flag register should be mapped. And the only reason, I mean, at least the reason which I know, is code segment, and it's kind of R flags mask. And the mask is to essentially disable interrupts. Because what if, I mean, we don't really know, maybe interrupts, I mean, they were definitely enabled when the user was running, because we want to receive a timer interrupt, unless we configure a system which uses non-maskable interrupt for timer. So essentially, but on entry, just because it's hard to enforce synchronization, if not impossible, in some cases, we immediately disable the interrupts by setting that the interrupt flag will be disabled. So only 3 things, right? And now you try to guess, how do we locate the kernel stack? We have the entry point of the kernel. We have a code segment, sure, which is mysterious, but CPU cannot run. One would assume, yeah, sure, like say once, no TSS, nothing. So where do we get the kernel stack? What are the possible options if you're designing a CPU? What do we do? I agree with you. Yeah, so the assumption here that the hardware, they said this time Intel did well. They said, okay, like forget about walking the TSS. Really, you don't need the stack when you enter the kernel. You can have a short trampoline when you execute the handler. And as you say, you just say, look, I have some address of the stack, like a global variable, and you have just instruction which
moves this into like RSP register.
And after that, you have a stack. So really, it can be done in software, very much similar to how we just agreed that we can do it at user level. So essentially, on entry into the handler, instead of assuming that the hardware will switch a stack, they delegated it to software. It's kind of a clever design because, well, maybe you're so clever that you can run a short sequence of code without a stack, but also like again, like it just makes the hardware simpler and they can optimize it more aggressively. And in software, this is like just much easier to figure out where this stack. Okay, I'll stop here just because it's probably time to stop. But essentially, the idea for the next time to go through the implementation of the system calls. It's honestly not hard, just a couple of hardware mechanisms, but there will be some interesting core cases. And after that, we'll have system calls. And this is like state of the art, how Linux does it, and other kernels which run on x86. And again, opens the door for like this aggressive optimizations where you really want to build very fast system calls. It's also possible, which we will have to do to build for fast inter-process communication. Okay, so then